Good morning, Internet. I am Matt Buyak, and in this video, I'm going to show you how to break RNG-based encryption schemes in the video game Super Mario Maker. Now, I will admit up front that I actually know very little about Super Mario Maker, but I do know a lot about algorithms. Recently, I was watching a video about the quest to create an unbeatable level in Super Mario Maker, and not just by making a level that was very, very difficult, but actually by using concepts from computer science and computer security. At the end of the video, its author, Ceave Gaming, I hope I'm pronouncing that right, presents a level that they've designed and claims that it is unbeatable. And my first reaction was, well, I can break that. Now, I don't want to be too hard on the original video because it's actually quite good and covers some fascinating topics. I'll put a link in the description so you can check it out. Now, your first thought might be that making an impossible level in any platforming game is trivial. Just lay down a bottomless pit or a bed of spikes or some other insurmountable obstacle and there you go. Impossible level. But in Super Mario Maker, in order to upload your level for others to play, you first have to complete it yourself. So the strategy of just making a very, very hard level is unlikely to succeed. Another common approach is to have some complicated mechanism out of sight of the player that obfuscates the details of what Mario needs to do to win. But somebody can just open the level editor and then the game is up. This gets to the foundational idea of computer security, which is that security through obscurity is no security at all. And to the credit of Ceave Gaming, they actually did an entire video on this idea, going over some of the schemes that players had come up with in the past and showing why they were all doomed to failure. So in order to make an unbeatable level in Super Mario Maker, we would need to come up with a system where even if the attacker knows all the details of how it works, they still can't break it, unless they have the password. Now, fortunately, cryptographers and software engineers have already invented systems like this. They rely on the idea of a one-way function, also known as a hash function, which is just a function that is not too difficult to compute, but very difficult to reverse. Let's see how this might work. Suppose my password is correct horse battery staple. Google that if you don't get the reference. And after putting it through my one-way function, I get the hexadecimal number you see on the screen here. I don't store the original password, I store the output of the hash function. That way, even if somebody gets a hold of that value, they still don't know the password. And later, when you want access, you still have to send me the original password. I don't even have the original password, but I can still verify that what you've given me is. So if somebody could implement a one-way function in Super Mario Maker, they would be able to construct an unbeatable level. And this is essentially what Ceave Gaming has attempted to do. His idea is that you're repeatedly presented with a pair of doors, and at each step you can choose to go through the left door or the right door. Each choice leads to a different sequence of events, which has some effect on the game's internal state. I'll get into more details on that in a moment. In either case, you find yourself back at the same pair of doors presented with the same choice. Then after some number of times through the loop, Mario is allowed to continue. And depending on the game's internal state, which was affected by the choices that you made, Mario either wins or he dies. Now, there's nothing wrong with this approach in principle. Depending on the details, it could either be very secure or not secure at all. Unfortunately, it turns out to be the latter. The problem is that the hash function built by Ceave Gaming is based on the game's random number generator. This is basically just an infinite sequence of values that seem random but are actually completely deterministic. That is, you can use them to decide whether an enemy goes left or right in a way that seems unpredictable to the player, but will actually cause the same behavior every time if you give the same exact inputs. It's actually important that the random number generator be deterministic in this case, because otherwise you might be able to create a level that could only ever be beaten at one specific time on one specific date. which presumably Nintendo doesn't want. In any case, the idea is that visiting a room with a bunch of clown cars will advance the random number generator a random number of times, where the exact number depends on how many clown cars are in the room and also the current value of the random number generator. Then at the end of the level, it sets up this trap where Mario only survives if the random number generator is at a specific point in its sequence. It's very complicated, and again, I would recommend checking out the original video if you want all the details. But the good news is that, for the purposes of our analysis, we don't actually need all the details. We only need to assume 3 things to show that this system is insecure. Number 1, the random number generator produces the same exact sequence of numbers every time. We've already said that it does. Number 2, the random number generator only advances one number at a time. That is, there's no way to skip forward to the 1 billionth or 1 trillionth random number. Our only option is to go through them in sequence. Number 3, the total number of calls to the random number generator is small-ish, say less than 1 million. Just for reference, the numbers given in the original video suggest a maximum of 10,000 calls to the random number generator, which is well within our limit. So let's get into the details of how this attack will work. The technique we'll use is called dynamic programming, which involves constructing a table of all possible states for whatever problem you're trying to solve and filling out the information for each cell in sequence. That might seem like a pretty unimpressive idea, maybe no better than pure brute force. So let's work through an example, and then I'll explain why this technique is so powerful. First, in order for it to fit on the screen, we need to make things much, much simpler. So instead of a 65-step hash function with 10,000 RNG calls, our example will have just 4 steps with a maximum of 12 RNG calls. Also, instead of having each of our 2 options lead to some incomprehensibly complicated sequence of calls to the random number generator, our choices are going to be to make 1 or 2 RNG calls if we go through the left door, or 1 to 4 RNG calls if we go through the right door, with the exact number depending on the current RNG value. Now, as I said, the table on the left represents every possible state of the hash function, with the columns corresponding to the number of doors we've gone through and the rows corresponding to the next value in the RNG sequence. We'll begin at the cell at the top left, which corresponds to having gone through no doors and having made no calls to the RNG. And suppose the RNG value that lets Mario live is this one here. That means we need to manipulate the hash function so that after 4 turns, we end up in this cell in the last column. To figure out how we might do this, we'll scan over the table from left to right, working out all the possible transitions from the states we're able to reach. For the first step, we have to start at the beginning of the RNG sequence, so let's see what states we can reach from there. If we pick the left door, we'll make 1 RNG call and advance to state number 1. If we choose the right door, we'll make 4 RNG calls and advance to state number 4. We'll mark both of these states with a 0 to indicate that they are reachable and that we arrived at those states coming from state 0. That completes our first turn, so now we'll scan down column 1 until we find a reachable state. In this case, state number 1. As before, we find the 2 states that correspond to our 2 options and mark them with a 1 to indicate that they are reachable from state number 1. I think you probably get the idea. We scan down to state number 4 and then mark rows 5 and 6 with a 4 to indicate that those states are reachable from state number 4. Continuing this process for columns 2 and 3, we eventually fill out the whole table. At this point, figuring out how to save Mario is easy. Remember, we're trying to reach state number 8, so we'll work backward from there. We see that state 8 is reachable from state 6, which is reachable from state 4, which is reachable from state 1, which is reachable from the initial state. Now just reverse the sequence and the password is revealed. Now, even after seeing this example, it might not be obvious what the advantage of this approach is. But let's think about the running time of the algorithm. That is, roughly how many operations will it take to complete? Well, for the dynamic programming approach, we'll have 65 columns, one for each step in the hash function, with around 10,000 rows, one for each random number we might generate. That second value is just an estimate, but honestly it could be 100 times larger and it wouldn't significantly change our analysis. So that means we have around 650,000 cells in our table, and because we process each cell exactly once, the total running time of our algorithm should be proportional to 650,000. For comparison, if we were to try the naive approach, where we simulate every possible way of choosing doors, that would involve checking 36 quintillion, 893 quadrillion, 488 trillion, 147 billion, 419 million, 103,232 possibilities. So why is dynamic programming so much better? The key is to realize that even though there are a huge number of possible inputs, many of them are going to lead to the same exact place. That is, you'll end up on the same step with the same RNG value. Everything you do after that point is just duplicated work. The dynamic programming approach completely eliminates all that duplicate work, which is why it's so efficient. Now, we're almost ready to look at some code, but before we do, there are two more data structures we'll need to make our solution efficient. The first is a lookup table for our random numbers. That is, going from a particular point in the RNG sequence to the corresponding number is easy. We just call the random number generator. But going the opposite direction is hard. That is, given a particular value in the sequence, the only way we can find where it goes is to start at the beginning and call the random number generator over and over until we find it. That could take a very long time. Instead, we'll just do that once when our program starts, and after that, we can just use the table. The other structure we'll need is a list of all the transitions between different states. Remember that the only way we can get this information is by running experiments. We have to actually simulate how many times the random number generator advances when we go in the left door versus the right. We already know that's going to be very complicated, so we only want to do it once. We'll run the experiments for all the RNG values and store them in a table like this. Now, with that out of the way, I think it's time to look at some code. Okay, so I'm guessing we probably have some non-programmers watching this video, so I'm going to try to keep the coding part as accessible as possible, even for non-programmers. For those of you who are programmers, I'm going to put all the code up on GitHub, so you can browse that at your convenience. Link in the description as always. Now, I want to be clear exactly what this code is doing and what this code is not doing. I am not simulating the exact behavior of the Super Mario Maker random number generator. I'm not simulating the exact behavior of the clown cars in Super Mario Maker. I just don't have the details and information in order to do that. What I am doing is simulating something that behaves in a very similar way and demonstrating an algorithm that will work regardless of the details. That is, if somebody were to take my code and replace my fake simulation with the real simulation, the rest of it would work exactly as written. Okay, with that out of the way, let's get into the code. Now, the code is basically in three different files: decrypt, encrypt, and common, with encrypt doing the encryption, decrypt doing the decryption, and common being the code that's shared between them. Right now, I've got encrypt.cpp up here on the screen, and you can see that it doesn't seem to actually be doing very much. Mostly, it's just checking to make sure that your password is well formed. It needs to be a string of L's and R's indicating at each step whether you go in the left door or the right door. Most of the actual work is done by calling this doLevel function down here, which is going to simulate the effect of the level on the random number generator. Then we call RNG.get to get the next value in the RNG sequence, and then we just print that out. So let's jump over to the common code where doLevel is defined, and we can see that this is just looping over every character in the string and either calling left door if it's an L and calling right door otherwise. And then right up here we have the definitions of left door and right door, with left door calling some function called clown cars with the argument 4, and right door calling clown cars 40. That's because if you go in the left door, you go to a room with 4 clown cars, and if you go in the right door, you go to a room with 40 clown cars. All right, so let's go up here and we see clown cars is defined, and it's going to loop a number of times equal to the number of clown cars you gave it, so either 4 or 40 clown cars. And for each one, it's going to pick a random number from 0 to 3 using the current value of the random number generator. Then based on that value, it's going to make 0 to 3 additional RNG calls, and so have some effect on the random number generator. This isn't, I didn't just make all this up, by the way. This is based on the description in Ceave Gaming's video of roughly the effect that the clown cars have on the RNG. But as I said, this is not the exact behavior. This is just an approximation. Okay, so that's how the encrypt side works. Let's go over to the decrypt side. This is really where most of the heart of the project lives. As I said, in our example, we're going to start by building this lookup table where we iterate over all the RNG values and we add the value along with its position in the sequence into our lookup table so that we can easily figure out, given a random value, where it falls in the sequence. And then the first thing we do after that is to do exactly that with our target RNG value. You can see we're calling lookup.find target. That's going to take the RNG value that we're trying to get to and return the number of RNG calls that we're going to need to make in order to get to that target value. Now, most of the code here is actually going to be building up our transitions table here. The idea is that we're going to iterate again over all the RNG values, and for each point in the sequence, we're going to first call left door, get the next RNG value, look it up in our lookup table, and that's going to tell us how far the random number sequence advanced based on this call to left door. One thing that's critical is you'll notice we don't assume anything about how left door behaves or what it's doing. It's a complete black box as far as this code is concerned. It just knows the RNG value beforehand, it calls left door, and then it checks the value after. And that's how it knows what effect it's having. And we do the same thing for right door down here. And then at the end of this loop down here, we're going to call this transitions.pushbackOptions to add both of our two options to our transitions table. Okay, so then we get into our dynamic programming algorithm proper. This T is going to be our dynamic programming table, T for table. And we're going to start off by resizing the rows and columns to the right size and setting the initial state to 0 to indicate that we can reach that state. The convention that I use is if a cell has a negative value, that means it's unreachable, and if it has a positive value or non-negative value, that indicates that it is reachable. Then here is the main loop where we're looping over each of the columns, and then within each column going down the rows to examine each cell. For each cell, we check to see if it has a negative value. If it does, that means it's not reachable. We skip it. That's what this continue is indicating. Then we get our left and right options, and we set the corresponding cells as reachable from the current cell. That's setting it equal to J. J is basically the current state. And then once we've looped over the entire table, now we're ready to retrieve our password. So we go down here, there's another loop. This one's going to be looping over the columns in reverse, just like we did in the example. We start at the target row in the last column, and we're going to work our way back to the initial cell, working out each character in the password as we go. But once we've done that, you'll recall the password will be backwards because we built it up in reverse. So now we need to call this reverse to flip it the right way around, and then we return password. And that's essentially our decrypt function. Okay, so now I think we're ready for a little demonstration. Let's go back over to our encrypt file. I've prepared a password up here that is just a random sequence of L's and R's. I used the website random.org to generate this. Unlike the random number generators we've been talking about, random.org generates true random numbers, which can be important for computer security applications. Okay, so let's open up a shell, and we're going to say make to build our project. There we go. And now let's try our encryption. We just give it our password here, and it spits out a number. This is going to be the random number generator value after the level has been simulated. So now let's see if our decrypt function can decrypt that. If we just run it with no arguments, it's going to helpfully tell us the information we need to give it. So first we need the number of steps. That's going to be 65. That corresponds to the number of characters in our password up here. Then we need the maximum number of RNG values. We estimate 10,000, so we'll do that. It's you don't need to be exact with this. If it's too large, it will just make the program run slower. If you put in a number that's too small, though, it may fail to find a password. So we'll put in 10,000 is our estimate, and then we're going to put in our target RNG value, which is this value right up here. That's going to be 823098032. Now, you will notice that this password does not match the password that we started with. So is our program broken? What's going on? Well, let's grab this new password real quick and try running it through our encrypt program once again. And we see that it puts out the same value. That's very interesting. This is called a hash collision. We have two different passwords that give the same RNG value as a result. And if we were actually playing the level, that means that both of these would solve the level. There's more than one solution. And this is kind of the fundamental problem with this approach, is that there aren't actually 38 quintillion possibilities. Many of them are actually equivalent. Okay, so before I sign off, I do want to say that my goal in making this video is not to tear down Ceave Gaming and the work that he and others have done. Quite the contrary. I want to see them succeed. I want to see that truly impossible Mario Maker level based on some kind of modern hash function or something like that. I wish them the best of luck. Now, to the rest of you who made it all the way to the end of the video, thank you so much for watching. If you haven't already, I hope you would consider subscribing. And if you do, I'll see you in the next video.